Okay, here's a recreation of the graph we had for our bouncing baby situation. What kind of favorite function would you like to use to model this? Well, most people say a sine wave, so sine of t. Now, does a sine wave perfectly describe what's going on here? Well, we have to think. Sines usually go between plus and minus 1, and they're centered on 0. This is not centered on y equals 0, and it doesn't go plus or minus 1. So what can we do to adjust this? Well, we could put an amplitude on it of 0.8, and right now it'll have an amplitude, a slightly smaller amplitude than 1, but we also need to shift the whole thing up. So we could put like plus 115. That's a vertical shift. So that's good so far. We've got an amplitude. We've got a sine wave going on. Is there anything else we need to do? Well, if you were looking at the video fairly closely, you were probably noticing that it was bouncing about 2 times per second. It was a very small bounce, but at fairly high frequency. So I need some kind of frequency term here. So I'm going to put a 2 and say 2 bounces per second. So it was 2 bounces per second. Different babies like different bouncing rates, by the way, and different amplitudes. But does that mean I put a 2 here? Well, we have to stop and think. What does it mean to have like a 1 here? How many bounces do you get per second there, or how long is it per bounce? And what if I put a 2 there? So let's think carefully about hold on. Okay, so let's think carefully about the frequency and the wavelength. So wavelength and period are pretty much the same thing. If I have sine of t, or just sine of 1t, what's the wavelength of that? So it has a frequency multiplier of 1, but what's the wavelength? Just a plain old sine wave does this, and it gets to 2 pi. So it has a wavelength of 2 pi when the frequency multiplier is 1. What if I said sine 2 pi t? That has the same look to it, but its wavelength is only 1, because when t is 1, then we get a 2 pi inside the sine, which means it's acting like this. So if I want to choose a specific wavelength, I have to make sure that I have kind of the right factor of 2 pi hanging around. So let's say to get a wavelength of, well, if I have 2 bounces a second, what's my wavelength? How long does one bounce take? That the bounce includes the up part and the down part. I'm doing 2 of those a second, so I'd have a wavelength of 0.5 seconds. I need 0.5, I need t equals 0.5 to act like 2 pi is acting there. So when t equals 0.5, I want the thing inside the sine wave to give me 2 pi. So let's think, does this do it? 2 pi over 0.5 t. So when t is 0, what do you get there? You just get sine of 0, which is what we expect. When t is 0.5, then the 0.5 here cancels the 0.5 here, and you get sine of 2 pi. And that should work out exactly right. So we'll get a wave that ends at time 0.5. So this ability to design a frequency multiplier term to give the exact wavelength you want is a pretty important skill. So we're choosing a multiplier to give the exact wavelength that we want. Now, I admit in this case, the frequency, the wavelength of 0.5 seconds was not precisely measured, and it's probably a little different from bounce to bounce. But there are times when you want that wavelength to be very, very precise, and in those cases, it's not sufficient to just kind of play with Desmos and choose a number here that gives kind of the right wavelength. You really need to think about what exactly the right wavelength you want is, and use this formula to get exactly the right wavelength in your sine wave. Let's wrap it up here with thinking about sine waves or cosine waves in general. We usually have an amplitude times a sine wave with some frequency multiplier times t. This frequency multiplier letter that I'm using is called omega. It's common in electrical engineering and such. And then we often have a phase shift, which I'm using the Greek letter phi for, plus some vertical shift. There's no common single letter for that I know of. So this A is the amplitude. This letter omega is a frequency multiplier, but it's not actually the frequency in seconds. You could say it affects the frequency. Some people do call it the frequency term, but it's a little weird because if omega is 1, then your wavelength is 2 pi, and so your frequency is 1 over 2 pi cycles per second. So that affects the frequency and wavelength. This phi is a phase shift. In radians, so it's kind of hard to work with. Like, you could let it be 2 pi or negative 2 pi or something. We'll talk more about that in a sec. And then the vertical shift, some other names for this are vertical centerline. Or in electrical engineering, it's called the DC, like direct current offset. If you have some kind of alternating current going on, but you add a constant voltage to it, that constant voltage is causing a direct current along with the alternating stuff. So you'll see that in more engineering-minded communities. If you don't want to deal with radians, I completely understand. There's a few ways to do phase shifts without doing radians. Obviously here, instead of sine, we could choose cosine. So that's one way to do a phase shift. Or you could use negative sine or negative cosine. So we know cosine does this, negative sine does this, and negative cosine starts low, goes up high, and then comes back low again for each cycle. So one way to choose a phase is to just choose one of these 4. Or you could do A times sine omega, and then instead of t plus phi, you could do t usually minus horizontal shift plus vertical shift. And that horizontal shift is then measured in the same units as t. So if t is in seconds, horizontal shift is in seconds rather than radians. So that's often a nicer way to do stuff. So we'll say in the same units as t. All right, so that's a way to get sine or cosine waves to do what you want, doing some vertical scaling, vertical shifting. This is horizontal scaling, and this is horizontal shifting. There. So go have fun with sine waves.